Chapter 5, page 12. This is the last page in the chapter notes, so let's go ahead and go over this. Now, we've talked about enantiomers and diastereomers in this chapter, optical activity, chirality, a lot of different topics. But let's go ahead and get into some of the physical properties of different types of compounds. Physical properties of enantiomers and diastereomers. Remember, enantiomers are chiral molecules that are non-superimposable mirror images. And we've talked in the last couple of sections that enantiomers have the same physical properties, except that one will rotate light in one direction and the other one rotates light in the opposite direction, plus they react differently with chiral molecules, other chiral molecules. So, enantiomers, they're mirror images of each other, non-superimposable mirror images. They have the same melting point, same boiling point. All the physical properties are the same, except one will rotate light in one direction and one will rotate light in the other direction. Diastereomers, on the other hand, will have all different physical properties. They'll have different melting points, boiling points, and you can separate them. We haven't done the lab yet on boiling points, but we have talked about crystallization. So if I have diastereomers, I can crystallize them separately apart from each other, but enantiomers you generally can't. Okay? Well, let's go ahead and get in how to resolve enantiomers. So, diastereomers have different physical properties, and I can separate them out because of those physical properties. But how can I separate out enantiomers? If I'm in a pharmaceutical company and I've just made a drug and one of the compounds in the enantiomers is a great medicinal drug and the other one's poisonous, how can I separate them out so that I can give just the one that has the beneficial properties and not have any of the poisonous compound in there? Well, there are two general ways to separate out enantiomers. Since they have the same physical properties, I can't crystallize them apart, or I can't separate them out by boiling points. But I can separate them out if I turn them into enantiomers, and so that's what this section is about. So take these two compounds right here, the R and the S 2-butanol, or butane 2-ol. They'll have the same physical properties. If I tried to boil them, they would generally come off at the same place. So I can't separate them out like that. But if I react them with a chiral molecule, and you don't know this reaction yet, I can react one of these oxygens here with one of the carboxylic acid groups. And what that will do is make a new molecule here, an ester. Now, because I've added a chiral molecule, I couldn't separate out the original R and the S compound. But if I add this tartaric acid molecule to it, now I've got multiple chiral centers in my new molecule. One has the S2-butyl RR tartrate, and one is the R2-butyl RR tartrate. And these are diastereomers. When some centers are the same and some centers are opposite, you have diastereomers. They will have different physical properties, different melting points, different boiling points. I can crystallize one away from the other one. And then, once I separate the compounds out, then I can do a reaction, split off the tartaric acid molecule, and then I have separate S compound or separate R compound in different containers. So I can start off with both of these compounds in the same container, and I can't separate them out because they have the same physical properties. But if I react them with another chiral molecule, I can turn them into diastereomers, and those I can separate. And then I can split the chiral tartaric acid apart and get individual S-butanol and R-butanol apart from each other. Then whichever one is the beneficial drug I can give to somebody, and whichever one is the poisonous one can then be destroyed. The other way to separate out enantiomers is by reacting with a chiral compound. So think of it this way. If I put in a mixture of the R and the S compound up here, or the dextrorotatory and the levorotatory versions, and then I had a bunch of little chiral molecules in here, think of it this way. If I had a mixture of my right and left-handed versions of the molecules, and in this chiral column there was little mini right-handed gloves, then the right-handed versions are going to get caught in the gloves more often than the left-handed ones. And one of them is going to be bound more tightly. The right-handed molecules will fit in the right-handed gloves. You can think of it that way. And they'll move more slowly. They'll still release from the gloves, but they'll move more slowly. The left-handed ones will move more quickly through it because they're not going to get caught on the right-handed gloves as much. And they'll come out at different points as they come down this column right here. Now, we haven't done chromatography yet. We're going to be doing it very soon in lab. But compounds will move at different speeds through this chromatography column. And the one that comes out first can be separated and put into an Erlenmeyer. And then when it comes out, I'll take this Erlenmeyer away, put a new Erlenmeyer underneath, and collect the other compound when its time is to come out of the compound column. So, the two ways of separating out enantiomers. Enantiomers have the same physical properties, but if you turn the enantiomers into diastereomers and then separate those apart, you can do that, or you can put the enantiomers into a chiral column and they'll move at different speeds through the chiral column, and you'll be able to separate them out that way. Those are the two ways, and that is the end of the chapter.